Welcome once again as we continue moving towards more advanced things. Do not get so worried about the word advanced, it simply means that you have some more additional information. That is what advancement means. Today we are going to speak about a very important result. Now many of you might think, oh, mathematicians are only bothered about some results and it has no consequence possibly in life. It might not have always a consequence in practical life, but sometimes these results can be used to prove some other results which might have consequences in your life. What does this intermediate value theorem says? It essentially tries to tell you the following. So, suppose if you have a function f from a b to r, right, and assume that it is continuous. Once you assume that, you have a huge information about the property of the function, the nature, and then it says that suppose you have the following information. This is a given information that f of a is strictly bigger than 0, f of b strictly less than 0, then there exists, this is a symbol for this, opposite capital E is a symbol for there exists x in AB, open interval AB, such that f of x is equal to 0. Obviously, this x cannot be any of the endpoints because the endpoints are not 0. So, this is what is called the intermediate value theorem. Does there exist one x only or does there exist more than one x? Let us draw some pictures to confirm it. For example, if you take a theorem like if you have a continuous function like this between a and b. So, this is your a and this is your b, where f of a is positive and f of b is negative, and here is this point x where it cuts the x axis. Means you start from the top of a mountain, you want to go below the river, then you really have to cross the surface of the river once. That is the basic idea. But that is basically, it means if you want to travel on the number line from -2 to +2, you have to cross 0 once. That simple idea is inbuilt here. Now, let us look at a situation where we can have more than one points where f of x would be 0. Some function could be like this. Never mind, you see f of a is still bigger than 0 and f of b, this is b and this is a, and f of b is still less than 0, but you have 1, 2, 3, 4, 5 points at which the function attains the value 0. So, here the statement says that there exists an x. It does not say that there exists only one x. So, here I want to make this fact clear that there can be more than one x, possibly could be countably infinite or uncountably infinite x's. For functions would look very complex, we are not getting into that. But this idea of continuity is very important. Why, I will tell you. For example, I will take a function f x which I will define from 0 to 1 to r, and I will define it as follows, that f x is equal to 1 when it is between 0, x and half and is equal to minus 1 when it is between half x and 1. So, you would immediately notice that here a is equal to 0 and b is equal to 1. A is equal to 0 and b is equal to 1. And what is f of a at 0? F of 1, f of 0 is 1, which is positive, and f of 1 is minus 1, which is negative. But let us look at the function values. Let us draw the diagram. But you can immediately see from the function, the values that the function is taking, there is no x for which the function has taken the x value, 0 value. Why it hasn't? It is simply because of the fact that in this line 0 to 1, so at this is the point half. So, up to half the value, so this is the demarcating point. So, here the value was 1, this is 1 and this is minus 1. So, it comes here and here. So, at half, exactly at half, it takes the minus 1 value and not the 1 value. So, this is the function value. So, you see immediately that there is a gap. This is a discontinuous function, and for a discontinuous function, the intermediate value theorem need not hold true. It may hold true also. I do not say it does not. For example, I will say f x is from minus 1 plus 1 to r. To r, and let me define it in this way. F x is equal to x when, see here you must understand that I am always not restricting f a to be strictly bigger than 0 or f b to be strictly less than 0. It could be the opposite. It could be, for example, that f b is strictly bigger than 0 and f a is strictly less than 0. Then also, so here you have f b to be strictly bigger than 0 and f a to be strictly less than 0. Then also you would have the same conclusion. There would be an x for which f of x would be equal to 0. What I am now trying to show you that these conditions f a, that this f a and f b are of opposite signs, that if I take the product of f a into f b, that would become negative. That is just a sufficient condition. It is not a necessary condition for such a thing to happen, that whenever I find there is an x between a and b such that f x equal to 0, it does not mean that this is going to happen, or the product of f a into f b would be strictly bigger than 0. So, this is one form of the theorem. So, to be more precise now you can write it in a better form, right, that if f from a b to r is continuous, I am writing for CONT for short, and f a into f b, the product is negative, then there exists an x lying in the open interval a b such that f of x must be equal to 0. So, this is a form which is much more acceptable, right. Now, here let me put f x equal to x when x is lying between 1 and 0, and f x equal to minus 1 when it is lying between minus 1 and the interval minus 1 0 excluding 0. So, this is the functional value. So, if I draw this, what does this mean? So, here is my say minus 1, so here is my plus 1, here is 0. So, you come from here. So, in this case f of b is plus 1, if I take b to be plus 1 and a to be minus 1, and then from 0 to minus 1 I put the value minus 1. So, here is minus 1. So, this is my function. This is of course a discontinuous function, it is not continuous, but you can immediately see that the conclusion that f x is equal to 0. So, here is an x between minus 1 and plus 1 for which f x is equal to 0. So, this, and also you see the product f of a which is 1, f of b is 1 and f of a which is minus 1 is minus 1. So, product is negative. So, this what I am trying to say is that if this condition, for example, continuity has failed, but this is true, then also this can remain true. So, these conditions that you see imposed here, that it is continuous and this product is negative, is a sufficient condition, means if this happens, then I am guaranteed that such a thing will definitely happen. So, this is something you have to keep in mind. These small examples actually give you much more better insight into what is really going on. And let us see, I will not immediately try to give you an idea of the proof. I am not going to do a proof of this, because everybody might not be adapted to or getting used to do mathematical proofs, though it is a necessary tool. But I would rather insist on concept building here in this course, with some cases coming to proofs, but I will try to give you some, first show some ways by which we can apply this result. Okay. So, let us see one of the first conclusion or consequence which I can draw from this intermediate value theorem. So, this is what I would call in short the IVT. Okay. Now, here is another form of intermediate value theorem. So, this intermediate value theorem, if I go a little bit into the history, was first shown or rather proved by Bernard Bolzano, and Bolzano, by the way, was a priest in the beautiful city of Prague, which is now in the capital of Czech Republic. And believe it or not, lot of very great works in science, for example, has been done by priests or monks, because for very poor people at those times, monastery was one of the places where they could get an education, they could get food, etc. So, in Europe, lot of very talented people, but not from a very rich background, went to these monasteries, and they really had time to practice science. And so, this was the contribution of Bernard Bolzano. So, let us see what is an immediate effect of that IVT. So, maybe first conclusion, I should write corollary actually, but I am writing it as a theorem, because this is what is written as IVT by many books. What I am going to now write down is IVT. So, let f from AB to R be continuous. Let C element of AB, actually open interval AB, be such that C strictly lies between FB and FA. You see, it could be opposite, it could lie between FB and FA could be strictly bigger than FB. Here I am just telling that, okay, let us just take it like this. Then there would exist X in AB such that Fx is equal to C. never mind, I want to tell you that this condition can also be written as, it could be of this form also, but just for the sake of showing how the result applies, we will just consider this form. Now, how do we go around and really prove something of this nature? So, in this case the natural trick, so here is a trick which mathematicians was used. What I know is that there would be a point f x is equal to 0 if I have 0, if I have the product bit of f a into f b to be negative, that is 0 should strictly lie between f a and f b, one is negative, one is positive. Then, but I now have c. So, what I do is, so if I want to prove it, so consider a new function g x, g whose all values are evaluated like this, f x minus c. Then let us look into what is g a is f a minus c, or what is f a minus c? F a minus c is negative, because f a is strictly less than c. And what is g b? f b minus c, which is strictly positive, because from this condition, because f b is strictly bigger than c. So, but because f is a continuous function, if you add a constant to a continuous function, it remains a continuous function. So, the first observation that we get from here is that g is a continuous function. Now, what is the product between g a and g b? Their product is strictly less than 0, because one is g a is negative, g b is positive. Now, this means, so hence now applying IVT, there exists x in this interval a b such that g of x is equal to 0, which would imply f of x minus c is equal to 0, which would imply f x is equal to c. So, what have we proved? That okay, if you do this, this is what is going to happen. You will going to, if this is the condition, by applying the IVT, by doing this little trick, a little translation, we can show just by a simple application of that, that there would always exist an x for which this happens. Okay. Let us look into another interesting consequence of this, right. So, can I prove this fact? Every positive number has its square root. If I tell you, okay, prove to me that every positive number has its square root, you would immediately try to take positive numbers and do the square root and say, okay, come on, it is obvious, you can calculate the square root of positive numbers, what is so big about it? But if I tell you to demonstrate to me that every positive number has a square root, right, then which means that you have to mathematically demonstrate that whatever positive number I give it to you, there is a number whose square is that number. So, if I give you any number alpha, you have to mathematically show me the existence of an x for which x of square equal to alpha. It is not that you will just sit down and start writing those you start trialing on, oh, 1 has a square root, 2 has a square root, it is not like that. In mathematics, you do not do such exhaustive things, you cannot do an exhaustive checks, because in calculus everything is infinite. Here this is the realm of the infinite, and hence a mathematical demonstration is very important, but we will see how this intermediate value theorem, or even this one if you want to say, actually shows you that you can really prove that every positive number has a square root. So, that is exactly what I am going to show you. So, this is a beautiful proof from the book of Spivak, and So, maybe if you want to call it a theorem, or mathematicians would call corollary, whatever you want to call it, it is a nice result. Every positive number, so every alpha in the natural number set has a square root, every positive real number, not in n, sorry, in R plus, means in the positive part of R, every positive real number has a square root. So, in order to prove this, what do I have to establish? I have to establish the following fact, that to establish. So, what is the thing that I have to establish? I have to establish the following fact, that given any alpha element of R and alpha greater than 0, there exists another real number x whose square is this number. So, x would be the square root of this number. So, there exists x element of R such that x square of x is alpha, which means x is the square root of alpha, right. Now, let us write down the function here. Let me consider the function f x is equal to x square, and alpha is a given number to me. So, now find b in R such that f of b is strictly bigger than alpha. If alpha is strictly bigger than 1, you could take b equal to alpha, because alpha square would be strictly bigger than 1. And if you want, if alpha is less than 1 and b 0, then you could take alpha equal to 1, because alpha square would be definitely less than 1, because alpha square would be less than alpha. So, whatever it is, you can always find such a number. So, here let me draw the diagram f x equal to x square. So, here is my alpha and here is my FB, this is my B, and here is my FB. So, FB is strictly bigger than alpha, but alpha being a positive number is, but since alpha is greater than equal to 0, it implies that alpha is strictly bigger than f0, because f of 0 is 0 here, because it is x square, f of 0 is 0. So, what do I find? F of 0 strictly less than alpha, strictly less than FB, but in the interval 0b, but f, if I just restrict it to the interval 0b to R, then this is also a continuous function. Now, once I do know that, and I know that this has happened, I can just apply what I have learnt here with a is equal to 0 and b is equal to b there, the same b. So, this would imply that there exists an x in the open interval 0 b such that f of x is equal to alpha, where this, and this obviously implies, because f x is nothing but x square equal to alpha. So, you see how beautiful mathematics is, that a so called advanced idea is actually needed to prove something which looks very obvious to you. Now, we shall go towards the understanding of the proof of this result. How do you prove it actually? But before doing so, I will tell you a story associated with this result. There is an interesting story, and many books write this story, but here I will speak from a book called The Concepts of Mathematics by Ian Stewart, about which I have already mentioned to you, but I would like to remind you and write down the name of this book, and I expect that every math student would get an access to this. Every school library should have it, every high school library, not school, rather college library should have it in India. Yeah. Unfortunately, not in any college which has money to buy books should have this book at least. It's a very cheap book at present. He is one of the most fascinating writers in mathematics, and is one of the leading mathematicians of our times. Sorry, Ian Stewart from Warwick University in the United Kingdom, and this book is published by Dover Publications. So, I begin by really showing you this book on the screen. I hope you see that. So, please consider, if there are some even teachers who are watching this program, please consider having this book in your library. It's a must for students and even in fact teachers to have a reading of this book. Math is not always about doing calculations or doing manipulations. Math is about developing ideas. A brilliant mind developing ideas in biology or mathematics is a brilliant mind. It is not that a mathematician who manipulates too many things needs much more intellectual faculty than a biologist developing a breakthrough concept. So here is the puzzle. The puzzle is the following. So I read out from this book, which says that at exactly 9 o'clock on Monday morning, a man sets off up the mountain, arriving at 6 o'clock in the evening. So a man starts. So here I can view on a horizontal plane the topography of the mountain. So here at 9 p.m. he starts climbing. At 6 p.m. he reaches the top of the mountain. Okay. And in the next day, okay, at 9 o'clock next morning, he descends from the same route, arriving at a point from which he set out at 6 o'clock in the evening. So 9 o'clock next morning, the graph would be like that. At 9 o'clock in the next morning, he sets out like this and climbs back to this point. Now the puzzle is the following: prove that at some time he is at the same place both the days. So there must be some point here, say some point on the mountain route where he is present, he arrives at the same time in both the days. So if he was at 12 o'clock in some place on the mountain route while going up, he is at 12 o'clock at that same place while going down. It might look slightly strange to many of us who has travelled up and down mountains. The idea is the following, that so this guy is now climbing down the mountain in the morning. So I assume that there is a ghost of this man who is climbing up this mountain, and he does the opposite journey. So some man starts at 6 in the morning and does the opposite journey, climbs up the mountain. So this is the path of this guy. So he starts at 6 and this guy has started at say 9 in the morning and he started climbing down. So another guy is actually now, so another guy has started at 6 and is climbing up. So there is a time you see. So here is the up path, here is the down path. So in the down path, what the guy is doing, he is climbing down. You can think of it as a ghost. The down path, so in the down path, this guy is coming down at starting at 9 and he is coming down. But think that there is a ghost who is also walking up the same path the next day towards the top of the mountain. Then you see that there is a time when both of their paths cross, which means the ghost and the man should be face to face at that point. So this is nothing but the intermediate value theorem, And what is this form of the intermediate value theorem? So, we will just write down how can I write this thing. So, this is a particular way of talking about the intermediate value theorem. So, this is something like this. See, if these curves were not continuous, if the mountain profile was not continuous, such things would not happen, as I have already shown. But here the mountain profile is also continuous. So, this is an application of the intermediate value theorem, that there exists a point between this where you would get whatever be the point, there would be a point where time point where this particular point would be reached in both ways. So, this can be actually expressed in the following way. This idea, this is the trick behind proving the intermediate value theorem, because I can write the intermediate value theorem as the following. So, I will have two functions f and g, and they have very opposite behaviors. The behavior is this: f of a is strictly less than g of a, but f of b is strictly bigger than g of b. So, this let me just draw the graph of this here. So, if two functions say between a and b, so here is my a and here is my b, right, f a and f b. So, the function value at a, suppose this is my f, the graph of my function f, this is my f function f x. And in case of g, you know that f g of a must be strictly bigger than f of a, but g of b must be strictly lesser than f of b. So, this is my g. So, there exists a point c between a and b where f x must be equal to g x, and that is exactly this puzzle, right. Here, because if you look at the mountain in this way, though it has one functional graph, if you look at the mountain in this way, it has another functional graph, and they have the same properties. So, this idea, so what happens now, I consider a function h whose h x is given by f a minus g a, right, is given by f x minus g x. So, this function h is a continuous function between a to b, because f and g are continuous functions between a to b, and difference between two continuous functions is again a continuous function. So, these are simple facts. Now, what is h of a here? H of a here is strictly less than 0, because f of a is strictly less than g of a, but h of b is strictly bigger than 0, because f of b is strictly greater than g of b, which would imply again by using IVT that there would exist an x in a b such that h of x is equal to 0, which implies f x is equal to g x at that point. And that is exactly the solution to this puzzle, because while going up the mountain profile would look as f, while going down the mountain profile would look as g. So, there are many ways to view this simple thing. So, how do you actually would prove it? I will not really get into the main idea. The proof essentially is the following. You divide, say, the interval a b into say 10 or 20 equal partitions, equal small intervals. Look into now for the first starting intervals, you will observe, because of the property of continuity, that if the difference of if h a is strictly less than 0, so in a neighborhood h a would continue to remain strictly less than 0. So, for some time you will have f x values strictly less than g x values. But then look at the first interval where you find a value of x for which f x value is bigger than g x value. Keep on dividing, now divide that interval again. and among that interval first find, so first find the interval where again f value is less than g value. So, you make this interval smaller and smaller and smaller, right. So, you in this interval first find those values for which f means you have now divided it equally, again find the case where you first find an x for which f x would be bigger than g x. So, take that small take that small interval equal on both sides and then again divide it. So, you will keep on having the smaller intervals and smaller intervals, basically you will take intersection of intervals. So, you will have smaller intervals and smaller intervals and smaller intervals, and which will silently close in on the point C at which f x is equal to g x. So, this is the idea which we are not getting into, but one application, the last application, of very important application is the idea which we will talk to you now, and that will be the last thing that I speak here as an application of the intermediate value theorem. It is called the fixed point theorem. Fixed point theorem tells me, suppose I have a function of this nature, that f is from 0 1 to 0 1 and is a continuous function. So, here is my 0 1 on the x interval, here is my 0 1 on the y interval, maybe it will be slightly on this side. So, basically I have this square. Now, I have some continuous function, some f is continuous, means is domain is 0 1, codomain is also 0 1. What I am trying to say is that the fixed point theorem says is that there would exist an x element of 0 1 such that f of x would be equal to x. Now, of course, this function could have f0 equal to 0, so it is done, or it could have f1 equal to 1, so it is done. The question arises, if not, if f0 is not 0 and f1 is not 1, the function should always have a positive values. So, this whenever a point remains fixed under the application of the function, such a point x is called a fixed point. So, what does it have got to do with the intermediate value theorem? But look at what we have just learned. Consider my function f x is equal to f and consider another function g x is equal to x. F x is the one which I am given and considering the function g x equal to x. Now, f0, if f0 is not equal to 0, then f0 must be strictly bigger than 0 because the function has to lie between 0 and 1, it cannot be negative. So, f0, so the function value f0 must be strictly bigger than 0, right. That is, f0 is strictly bigger than g0, this implies this. And what is f of 1? F of 1 cannot be more than 1, f of 1 has to be strictly less than 1. Either it is equal to 1, then it is done. If it is not equal to 1, then it has to be strictly less than 1 because the function value must be within 0 and 1. And in that particular case, I will just rub this part. So, I will just do it for you again. So, what is happening here? So, I have taken f x as the function, f is the function, functional values of f, and for me g x is equal to x. Now, let me say that f0, let me be in a situation where f0 is not equal to 0 and f1 is not equal to 1, because if any of these conditions happen, then this result is true. Then in this case, f of 0 must be strictly bigger than 0, which implies that f of 0 is greater than g0. because f0 is not equal to 0 and the function is between 0 and 1, which is non-negative. So, it has to be strictly bigger than 0, but f of 1 has to be now strictly less than 1, because the functional value cannot exceed 1 and f 1 is not equal to 1, which implies that f of 1 is strictly less than g of 1, which is 1, because g x is equal to x. So, it is exactly in this situation. It is exactly in the situation of this mountain climbing situation. So, you will immediately prove that there would be an exist an x between 0 to 1 such that f of x would be equal to g x, but g x is equal to x. So, this would imply that f of x is equal to x, and voila, my theorem is proved. Voila actually is a French word, which means that is it, done. So, you see how we have built up the whole story and surround it with this simple man climbing up the mountain, which can come and prove this fact. It looks very obvious, because you can draw this line y equal to x here, and a continuous function you would feel would cut across this y equal to x line if the function range is also between 0 and 1. Now, fixed point theorem, you might say what story you are talking about, but let me tell you, a huge amount of modern economic theory, and economics is of course practical stuff, is based on fixed point theorems. So, with this I would like to end this class, and I hope you had enjoyed it.